We are studying neutrino spin and spin flavor mixing and oscillations in a constant magnetic field with a twist, in a twisting constant magnetic field. So, and we reached the level when we determined or derived the equation of evolution of two flavor neutrinos of two different flavors with different spin orientations. And we have derived this equation, and we were just studying to find a solution for neutrino probability, oscillation probability for this particular case. So, the evolution equation of neutrinos with non-zero magnetic moment in twisting magnetic field. That is like modulus, let's say, and this depends on time. Yeah. So we have derived. So we introduce the magnetic moments in the mass states of neutrinos for particles with well-defined masses, and introduce electromagnetic interactions for the mass states. Then we make a transition to the flavor states and have reached and just derive this equation I'm going to write now. So I d over t. So we consider two possibilities: neutrino electron flavor left to neutrino muon flavor right. So this is mixing and oscillations of flavor neutrinos with different spin orientations. We consider relativistic neutrinos, and we are dealing with the chiral or helicity states. It's more or less the same, yeah, more or less the same for this particular case. So we expect that there is a mass square difference of neutrinos. There is also interaction with media composed of electrons, neutrons, and protons in normal matter. And also there is an effect of twisting. This is a constant magnetic field, but the vector is changing in space. From point to point, it is like a rotation, but it is constant in time. So here is minus delta left right. I just recall what it is, divided by 4 neutrino energies. Sigma 3, this is Pauli matrix, plus the effective magnetic moment in the flavor basis. This is transition, really, magnetic moment, that, as you remember, is determined by the fundamental magnetic moments introduced for the mass states of neutrinos. The strength of the field, of magnetic field, sigma 1, nu electron left, nu muon right. That is the solution. This is the equation we have derived, where this delta left right equals to, the first term comes from the flavor mixing, normal mass square difference multiplied by the cosine of the double mixing angle. Mass square difference cosine double theta minus 2 neutrino energy is 0. The potential of active electron neutrino plus 2 multiplied by the energy phi dot. Mass square difference, as usual, mass square difference equals to the mass squared of the second neutrino, mass squared of the first neutrino. So this is the equation we have derived last time. So, and the solution as it was in a familiar for us case of Lefebvre mixing and oscillations can be right just in the following way: electron left, muon right, as a function of x in some particular point equals to exponent minus I, then minus delta L R divided by 4 energy of neutrino, sigma matrix 3 plus the effective magnetic moment, mu electron muon, the strength of the field multiplied by sigma 1 x multiplied by the initial state, by an initial state of neutrino that is nothing but electron left in the coordinate x equal to 0, muon right 0. Okay. So we know how to operate, how to treat the exponent that depends on the matrices. Yeah, we discussed it last semester. So I make plus. I only recall a very powerful equation: exponent minus I sigma vector on some vector A, let's say, yeah, multiplied by phi equals to cosine phi. I am missing here the unit matrix, yeah? I am not writing the unit matrix. Plus I, minus, because here we minus sigma I sine phi. This is very well known for you. Formula from quantum mechanics. Yeah? Okay. So just using this and applying this to our case, we introduce the following notations. So introduce omega squared equals to magnetic moment multiplied by the field squared plus delta R L R divided by 4 energy squared. And also we introduce a vector K with the following components, three-dimensional vector. The first component mu multiplied by magnetic field, the second 0, and the third one is minus delta LR divided by 4 energy. So we introduce these notations and new values. It can be easily seen that k squared equals to omega squared. then K multiplied by sigma matrices equals to exactly what we need to have, magnetic moment multiplied by the field sigma 1 minus delta LR divided by 4 energy sigma 3. We have prepared everything to use this formula to write in a very convenient form the solution for the neutrino evolution equation. Yeah? So we can write that nu in some point characterized by the coordinate x, that is, I just write once again, electron left-handed neutrino, muon right-handed neutrino, and the solution can be written in the form exponent minus I omega multiplied by x then I just put here k divided by omega sigma vector. This is the scalar product of the really this is a unit vector, yeah, multiplied by a vector with components of sigma matrices, and here this is the initial neutrino state, that is electron 0, muon right-handed 0. Yeah? And just applying this very nice formula, very powerful I should say, we can just go further, please, and write finally in a very, very similar way. We have derived the same expression for the evolution equation in the when they discussed the mixing of flavor neutrinos. Yeah? This cosine omega x minus I divided by omega, here delta LR divided by 4 energy multiplied by sigma 3 minus the effective magnetic moment of neutrino, the strength of the field sigma 1, and everything is multiplied by the sine omega x. So we just make this, and this act on the initial neutrino state, that is electron left in initial position, muon right for x equal to 0. So, and the next step is just to write the probability of neutrino oscillation. And this is a process where flavor can be changed, and also the spin orientation can be changed. So, can I go further? Okay. Okay. The probability of neutrino oscillations. So, the probability of neutrino electron left to neutrino muon right as a function of x equals to the squared of the matrix element neutrino mu right state. This is neutrino electron state in the point with the coordinate x. Yeah? So we are looking for the projection to the right-handed muon neutrino in the solution of the evolution equation in the coordinate, in the position characterized by some coordinate x. We have derived this. Yeah? So let's write it explicitly. Modulus, that should be squared after 1, 0. This is correspond to the muon neutrino with the right-handed. Okay, spin orientation cosine omega x minus I divided by omega delta L R divided by 4 energy sigma 3 minus magnetic moment multiplied by the strength of the field and multiplied by sigma 1. Okay? And also should be everything should be multiplied by sine omega x. Okay. So we just close these brackets, and here we write 1, 0 modulus squared. Okay? So I just recall that sigma 1, 0, 1, 1, 0, sigma 3 is the diagonal matrix, 1, 0, 0, minus 1, and then it can be easily calculated, and we get the following, that this is magnetic moment multiplied by the field squared divided by omega squared sine squared omega x. If just to write it more explicitly, magnetic moment, the field divided by the sum of the same magnetic moment multiplied by the field squared plus delta divided by 4 energy LR squared sine squared omega x. This is the explicit expression for neutrino oscillations. Really, this is a spin flavor oscillations. So, in addition to the change of flavor from electron to muon, spin is also changing. Yeah? So, spin flavor oscillations. I would say this is a new phenomenon in respect to the flavor oscillations, because the flavor oscillations, the origin or the nature is due to inherent mixing that are introduced or described by the mixing angle theta. Yeah? Here the mixing is due to mixing between left and right-handed neutrinos due to non-zero magnetic moment interaction in transversal magnetic field. And normally people consider these two types of oscillations mixing and the oscillations like a separate phenomenon. Yeah? And I would like to recall the correspondence, in a sense, between these two effects first. And then I will add that they, as it was shown very recently in our papers by our student, or now postgraduate student, Artem Popov, and he is now going to defend his PhD dissertation, and one third part devoted to this particular issue. In fact, it is not possible to consider neutrino flavor and spin mixing and oscillation in the presence of magnetic field separately. So these two phenomena correspond to each other. And just to characterize this correspondence and the relation and communication of these two different phenomena by words, the fact is that in the presence of magnetic field, the amplitude of oscillations depends on the magnetic moment and magnetic field. So it is the amplitude is modulated by the frequency that is proportional to the product of magnetic fields on the magnetic moment, and vice versa. The amplitude of spin oscillations or spin flavor oscillations is modulated by the vacuum frequency that is determined by mass square difference and the energy. So to be exact and to say the real truth, you cannot separate these phenomena. Of course, we can speak about this communication, about this issue only in the presence of magnetic field, because if there is no magnetic field, then there is no mixing between left and right-handed neutrinos. But this is also not the very end of the game. Well, the fact is that, again, in our paper, just exactly 20 years ago, I have proposed another new phenomena, that the spin mixing and the oscillations can be generated or engendered without any need for non-zero magnetic moment and without presence of magnetic field. There is no need. But these spin mixing and spin oscillations between left and right-handed neutrinos can be produced by weak interactions, not electromagnetic interactions, by weak interactions of neutrinos with moving matter. In case when there is a transversal, not zero transversal component of matter in respect to neutrino propagation. This is exactly a new phenomenon, really. And it was predicted in my paper 2004, and then about 10 years after, and other people just tried to use this to the study of astrophysical neutrino fluxes that are produced under the influence of extreme astrophysical conditions where there are dense fluxes of media, probably rotating media, and there could be that neutrino is facing the transversally moving matter if there is a rotation of matter. Yeah? Understand? This propagates from inner part to outer part and perpendicular to the axis of rotation, and in this case the neutrinos see the rotating matter. It can be a matter of accretion disk or the matter of rotating star. But that is another game and another issue, and we shall also discuss this. So let's compare neutrino flavor oscillation probability of flavor oscillations and spin or spin flavor, spin I just recall the main formula for probability of neutrino flavor oscillations. Again, we are dealing with two mass states neutrinos and two flavor neutrinos, and the probability of flavor oscillations, neutrino electron to neutrino muon, as a function of distance, x equals to the amplitude of oscillations, sine squared double mixing angle, yeah, and multiply by the second sine squared, that is pi, travel distance x, divided by the length of oscillations. If matter is present, then we put here wave. Is an effective mixing angle in matter. You remember that due to interaction of electron muon neutrino with the environment, the matters, the effective mixing angle is changing. Yeah? And also here I just put the symbol m. It means that this is not a vacuum oscillation length, but it is oscillation length in matter, counting the matter effect. And I will just write this expression. The oscillation length in matter equals to 2 pi's divided by the energies of neutrinos of 1, 2 neutrino. Waves means that this is an effective energies accounting the effect of scattering of neutrinos on particles of environment, on matter. Yeah? And I will put here an expression that we have derived about half a year ago for this, just to recall, this mass square difference divided by 2 neutrino energy cosine double mixing angle in vacuum without delta minus square root of 2 the Fermi coupling J multiply by the number density of electrons. So we here suppose that matter is composed of electrons and neutrons with equal numbers per cubic centimeter, and also of neutrons. And we consider 2 neutrino flavor states, electron and muon, and if you remember, we carefully derived the contribution to effective Lagrangian. Then we derive the shift of potentials of electron and muon neutrinos due to scattering on this concrete type of matter. Therefore, here only the electron number density survive, only for this particular case. Yeah? We also discussed with you if we are considering neutrino effect active to sterile oscillations, like fourth component sterile, there will be also contribution from the density of neutrons. Yeah? You remember, yeah? Okay? So squared plus the last term here, mass square difference, delta m squared divided by 2 energy squared multiply by sine squared double theta. This is the effective oscillation length. Here I would like to write the spin flavor oscillation probability in the following form. I just introduce sine squared beta. I will just explain what is beta, but you can see easily. Well, so the correspondence between flavor and spin flavor oscillations can be summarized as follows. This is the amplitude of oscillations in the case of flavor oscillations, And here is the amplitude of spin-Flavor oscillations. And this term is determined by magnetic moment multiplied by the strength of the field divided by magnetic moment, the strength of the field squared, plus delta LR divided by 4 energy squared. So this is the key point. So in case of flavor mixing, the amplitude is determined by the given by nature, or put in the theory by hands. The mixing angle shifted by exact calculation of scattering of flavor neutrinos on particles of environmental matter. And this is an amplitude of oscillation also describes, this value describes the mixing between two species of neutrinos, left and right-handed, and also we are dealing with a specific case when also the flavor is changing. Okay, from here we can, like a more simple case, we can derive the spin oscillation probability when the flavor is not changing. It is just straightforward. Let's write spin oscillations. Spin. Spin oscillations in matter. No, we are considering here effect of matter at rest, without, plus magnetic field. So the mixing between electron left and electron right neutrino now is due to the diagonal effective magnetic moment of electron neutrino. And this value is also determined by the introduced initial magnetic moments for the mass states of neutrinos, neutrino 1 and 2, and there is also contribution, if not zero, from the transfer, not diagonal magnetic moment for the flavor states, mu 1, 2. If you remember, we have written these formulas that describes the effective magnetic moments in the flavor basis in terms of initially introduced magnetic moments for the mass states of neutrinos. Okay? Probably once I will repeat these formulas, but probably not now. So, this is just, we can, if you remember what is delta, we have to put mass square difference there to be 0. Yeah? Or not?
I guess so.
So, please, I just put here like a task. Please, it is very simple. Write yourself. One more comment regarding this probability of flavor, spin flavor oscillations. When the amplitude of these oscillations gets its maximum value. So, in other words, when there is a resonance. So, there are two terms here, and this is the amplitude of oscillations, and we term this situation when the amplitude gets its maximum value equal to 1, sine squared of something, the maximum value is 1, when this resonance can be achieved. So, when we have something divided by something plus extra term. when this value is equal to 1.
When
When the resonance in these oscillations, when delta LR comes to 0, yeah? Or, this is, okay, this is an extreme case, yeah? But when these oscillations will be visible or just sufficient, not small, yeah, not small. You can put a criteria when this amplitude is exceed 1/2 or 10%, depends how sensitive you are and how sensitive is your device, yeah, to detection procedure, yeah. Well, and we can say that the resonance is realized not only when delta is equal to 0, but when delta is much smaller than this guy. Yeah, so we can write that magnetic moment, effective magnetic moment multiplied by the strength of the field, should be much bigger than the modulus, because this guy can be, if you remember, can have negative sign, delta divided by 4 energy. So this is the particular cases when the amplitude of oscillations is not much smaller than 1. Yeah, it's reasonable value. This is the resonance. Yeah, this is in effect similar to the famous Mikheyev-Smirnov-Wallenstein resonance in the case of neutrino flavor mixing in the presence of matter. Also, matter can kill this term when this is the length, but the amplitude of oscillation also have in denominator this term. And when matter kills this guy, the amplitude of oscillations become equal to 1. That was Mikheyev-Smirnov-Wallenstein resonance. The same effect exists in the spin or spin flavor oscillations in presence of matter. Also, we include to delta LR also effect of phi. You remember, yeah? Also, this term can also destroy or just improve the resonance condition. Yeah, it's an additional phenomena, I should say. It depends on the structure of real magnetic field that can organize this oscillation resonance. And if you remember for sure Mikheyev-Smirnov-Wallenstein resonance amplification of flavor oscillations, but in case of spin flavor oscillations, this phenomena was first theoretically discovered in the paper published in 1988. There are 2 papers here really by our Evgeny Akhmedov and another paper, Lim and Marciano. There were 2 papers published in 1988 in one journal, Physical Letters B, and they predicted that there could be also resonance amplification of spin flavor oscillations. Very, very, very interesting phenomenon. Вообще хочу. Хорошо. Thank you. Спасибо. So, can I move further? Yeah. So, one more note I would like to advertise now. This is like notes. I would like to recall the Lagrangian of electromagnetic interaction that describes neutrino magnetic moment interaction with the external magnetic field and general electromagnetic field. So for our case, this is I write it for the flavor basis. Yeah, this is the constant is a effective magnetic moment in the flavor basis. Again, we confine ourselves to the two mass states and two flavor states, electron muon state, and this is an effective magnetic moment. Here is the field of electron neutrino. This is sigma mu nu, the tensor of electromagnetic field, and here is the magnetic, the neutrino, muon neutrino, and it is quite easy to show that this kind of interaction, probably we discussed this in one of previous sessions, this being together neutrinos with different helicities, left and right, or chirality, yeah, is because of the properties of this sigma mu nu, yeah. Yeah, so this is a sum of two terms, and just exactly mixing appears here. Electron left, sigma mu nu, F mu nu, muon right, plus magnetic moment, muon right, muon left, yeah, sigma mu nu, F mu nu, electron right. So, and we suppose that electron neutrino is a superposition of left and right-handed neutrinos, and the same is for muon neutrino, yeah? And also, it is possible to write the equation of for both these fields, for left-handed electron neutrinos. So we can write, just using this addition to the Lagrangian, we can write that the equations are the following. This is neutrino left equals to minus delta LR divided by 4 neutrino energy, neutrino left electron plus magnetic moment, effective magnetic moment, multiplied by the field B right-handed muon neutrino. So this is the equation of evolution of a left-handed neutrino when there is not trivial, not zero, magnetic moment mu E mu, yeah, transition magnetic moment, and the same is for muon neutrino. We can write the same similar equation. This is delta LR divided by 4 energy, neutrino muon left plus magnetic moment, the field strength, neutrino electron right. These two equations that is just straightforward from this Lagrangian. So I think that we shall now turn to another very interesting phenomena in neutrino mixing and oscillations, accounting for neutrino interaction with matter. And now we shall deal and treat the effect of neutrino mixing between different neutrinos spin states due to interaction with moving matter. Well, I have already introduced these phenomena, and like a very short introduction to this I will start with some historical note. So this is a new novel in our lectures, neutrino mixing and oscillations. In moving matter. I once again repeat the main result now, just to be very clear what we are eager to discuss with you. So there exists neutrino mixing and oscillations. I am not saying what kind of neutrino. Flavor, let's say, electron to electron left to electron right, let's say, yeah? Due to matter current with, this is transversal matter current. Transversal in respect to neutrino propagation. So we have a flux of neutrinos. This is momentums of neutrinos. This is neutrinos. And this is matter. And from interaction of neutrinos with transversally moving matter, and these interactions are due to weak interaction that determined by the Fermi coupling constant. There is no need for whether magnetic moment or magnetic field. This is zero, can be exactly zero. And even in this case, this is transition between left-handed electroneutrino to right-handed electroneutrino, or if there is a transversal contribution that can be transition from electron left to muon right. Both the spin and spin flavor oscillation can be produced. And at first, this phenomena was predicted in my paper published in Nuclear Physics, ядерной физики. And it was just as a result and introduction, it was formulated that the new phenomena in respect to what was considered before, that spin and spin flavor oscillations can be produced only by magnetic moment interaction of neutrinos with the transversal magnetic field. So there is no need, whether magnetic moment, no magnetic field, but if neutrino interacts with matter moving transversally, or if there is a transversal component, yeah, or also the same is transversal polarization. If matter is polarized, it was also mentioned in this paper, that whether the motion of there is a current, or matter can be at rest but can be polarized. The spins of particles of neutrons are polarized by some, I don't know, some mechanism in direction transversal to neutrino propagation. Also, there will be mixing and oscillations between different neutrino spin states. It's a very, very interesting phenomenon. It's completely new, by the way. But of course, it's very hard to. The density should be very, very high. Yeah. But and how I just come to this conclusion, to this fact. So in one of previous papers, together with my collaborator Andrei Lobanov, it was published just probably a year before. Yeah, it was published 2000. 2001. So there was a paper by Lobanov plus myself, 2001 and 2002. Right. Two papers. We propose a quasi-classical treatment of neutrino spin evolution in the presence of external environments, whether external electromagnetic field or external matter. So, and we really derive the generalized Barman-Michel-Telegde equation. If you remember, there is an equation in quantum electrodynamics, quasi-classical equation of spin evolution in electrodynamics that was derived by three people, Barman-Michel-Telegde equation. Yeah? Well, and we generalize this equation, for accounting for interaction of neutrinos by weak forces, weak interaction of neutrinos with external matter. We just add additional term to this. And this generalized, as we call it, Barman-Michel-Telegde equation Barman-Michel-Telegde equation for three-dimensional neutrino spin vector. So ds, three-dimensional neutrino spin vector, dt, evolution, 2 divided by gamma. Gamma is the energy of neutrino divided by its mass. Here is the spin B0 plus M0. This is what we, where B0 is the magnetic field in the rest frame of neutrino. B0. So, there are two reference frames, yeah? One is laboratory, when the observer is observing, yeah? And there is a reference frame related to relativistically moving neutrino, yeah? There are two reference frames. Now, let's suppose that there is electromagnetic field or magnetic field determined or measured, observed in the laboratory frame, yeah? And neutrino sees another field, and to understand and to get what is the field in the rest frame of neutrino, you have make a Lorentz transformation for the electromagnetic field. Yeah. So this is in the rest frame of neutrino. Yeah, in the rest frame of neutrino. Can I move further? So you can, if you not remember, I can write, or just you can check in the textbook. This vector in the rest frame of neutrino can be expressed in terms of electron and magnetic field components determined or given in the laboratory frame. Yeah? This is a gamma. This is transversal magnetic field in the laboratory frame plus 1 over gamma suppressed for relativistic neutrinos, longitudinal part of the field given in the laboratory frame, and plus also contribution from electric field. Yeah? So more complicated part of formula, 1 minus 1 gamma squared multiplied by the vector product transversal magnetic field multiplied by beta. Beta is the speed of neutrino divided by modulus. It's unit vector in respect to neutrino propagation. Yeah. So beta is velocity or speed. Gamma, where gamma is related, if you remember, to this beta. This is square root in the denominator 1 minus beta squared. Yeah. And beta is a neutrino velocity vector. Neutrino velocity in the laboratory frame. So this magnetic field that is seen by relativistic immovable neutrinos if there are these components of electric and magnetic fields are given in the rest frame of neutrino, in the laboratory frame. Yeah? And by the way, just taking into account this, especially this part of this relation, this expression, we see that always or oftenly the longitudinal part of magnetic field is neglected when we are considering neutrino spin evolution in the presence of magnetic field. Yeah? Because it is strongly suppressed by gamma. Gamma is, for relativistic cases, is much bigger than 1. This field is enhanced by gamma, and this is not enhanced. So the contribution of transversal and longitudinal parts of magnetic field is quite different. Yeah, and often people just forget about this. Okay. Well, and what is M in that generalized Bar-Michel-Telliger equation that we have derived with Lobanov, Andrei Lobanov? This is a staff member. He passed away last summer. I'm sorry. Yeah? So what is M? M, this is a method term. Method term. Also, we can distribute it to longitudinal part in the laboratory frame, yeah, in the laboratory frame vector, yeah, and transversal part in the laboratory frame, and we have derived exactly that was our result. M longitudinal, this is a matter term, equals to gamma multiplied by the vector of, this is the speed of neutrino, then n0 divided by 1 minus we, for simplicity, for like as an example, we consider that matter is composed of electrons, and in the laboratory frame it is described by the invariant number density in the laboratory frame. This is a number of electrons in cubic centimeter in the laboratory frame. And V is the speed of electrons. So that is the classical speed. This is not, if you have a gas of electrons, each of electron moving disturbed by a quantum distribution, but you should sum up, and this is just to understand, this is the classical speed of matter. So you have a tank or of matter that is moving at a whole. This is not macroscopic motion, yeah? This is a classical effect, yeah? Classical, because each of the particles can move individually, yeah? But you sum up all these, accounting for distribution function, yeah? And then calculate the macroscopic velocity or speed of matter, yeah? This is a classical phenomenon, yeah? Okay. Then, rather complicated expression. And this is a constant. I will just, we indicated rho 1 multiplied by 1 minus the vector product of the electrons multiplied by the speed of neutrinos divided by 1 minus gamma neutrino squared. Yeah? Minus another constant, I will just indicate it in a moment, 1 minus 1 divided by gamma squared. This is what I have mentioned. This is polarization of matter. Again, this is not polarization of individual electrons, let's say. This is a total polarization of the whole matter, yeah? It can be calculated due to two-step averaging. The first, you just use the spin operator for individual electron. You calculate the average value, and then you calculate the polarization of the whole ensemble using the statistical distribution function. Yeah, you understand? Yeah. Some people, by the way, very important, I should say, one of the authors of the Mikheyev-Smirnov-Alfvenstein effect. I don't want to say the name, but you can see in our paper. They also try to deal with this effect, but they do not distinguish the quantum averaging of spin operator for individual electron and the statistical averaging over the statistical ensemble of huge amount of electrons. Yeah, and they didn't distinguish. You understand? Yeah. And in some cases, they had a proper result. for prediction of this part will contribute to spin oscillation probability in some particular case for in polarized matter. In some cases, for some geometry of neutrino propagation in respect to moving matter and polarization, they get a proper result. But in some cases, completely not proper, and they discuss, and they even say we do not understand why this phenomenon is happening. Once I gave a lecture, and we discussed, and finally we find the common vision of this effect. Okay, but for us it's not important, but I would like to put it for completeness. This again, the speed of neutrino, this is 1 minus the speed of electron squared over electrons. This is a classical as a tank, yeah, as a carriage of electrons. Plus, again, this is polarization of matter multiplied by the speed of matter. This combination, the speed of neutrino multiplied by the speed of matter divided by 1 plus square root of 1 minus speed of matter. We close this, and also we close this. Yeah. Okay. Indeed, I just put it for completeness, but these terms are not of interest for us because, for simplicity, let's do not account for effect of polarization of media. It is too complicated. But I would like to show the kernel part of the effect. So that left and right-handed neutrino states are mixed, and the corresponding oscillations appear, spin oscillations, due to neutrino interaction with the transversally moving matter. This is my goal of now. And this guy describes the effect of transversally moving matter. So let's write this explicitly. This vector, 0 transversal, and I just will skip contribution from polarization effects, just to make it more simple and shorter formulas. Minus m n0, this invariant number density in the laboratory frame, divided by square root of 1 minus the speed of matter squared. Then the vector of the speed of moving matter, its transversal component. This is the guy that produced this mixing. Multiplied by some constant, we just indicated rho, plus terms proportional to polarization, or we just skip them. So this is not important. This is the key point. This is the key point. This is a contribution to this effective M that describes weak interactions of neutrinos of a particular type that we are considering with the moving matter. The first term, this due to interaction of neutrinos with the longitudinally moving matter, and this is transversally moving matter. And I would like to show what is this rho. Yeah, we have rho 1 or rho 2. I just write rho 1 here, where rho electron 1 equals to Fermi coupling constant divided by 2 square root of 2 neutrino magnetic moment. Don't be afraid about appearance of magnetic moment. I was always saying during the last 15-20 minutes that there is no need for magnetic moments. But this in denominator magnetic moment will be cancelled out with the magnetic moment with the general Barr-Machel-Telegin equation in nominator. So totally the contribution to the transversally moving matter will be free of any magnetic moments. It's cancelled out. So just using the Barr-Machel-Telegin equation, it is possible, I don't want to go further in some technical details, it was possible to derive the equation of evolution of two mass states, different mass states of neutrinos in presence of magnetic, electromagnetic field and moving matter. And I will write this equation. By the way, the point why we did not discover together with Andrei Lobanov effect of mixing and oscillations due to interaction with transversal moving matter was the fact that we derived this guy and this guy as an expansion over 1 divided by gamma. So these formulas were not used in our papers. We were sure that everything is suppressed by gamma in the denominator, because gamma is a Lorentz factor. We just neglected. We just write the first term plus terms proportional to 1 over gamma. And here also. But the effect is just in terms that are suppressed by gamma. So that's why in our initial papers we just always didn't have even no chance to see this effect. Now, only in 2004 I just derived the whole exact. It was possible to write just 2 years before, but we just were that when you are doing something for the first time, you are just trying to understand. There are a lot of discussions, etc., and we just survive. We don't want to go to some minor effects that we just neglect them. Yeah. Also, you know that when we are deriving this classical formulas for neutrino flavor mixing and oscillation, we also just confine ourselves to the first order expansion of a relativistic factor. Yeah, we say that the energy are equal, but they are not equal if you just write the next term. You see? Okay, and the evolution equation. The neutrino evolution equation. So let's say T, neutrino left, neutrino electron right. So for simplicity, we consider one flavor neutrinos. Yeah? Electron left and right neutrinos with not zero magnetic moment, yeah? And coupled to matter. This is mu, and here we have 1 over gamma modulus m vector m 0. That's all. I think that, okay, let's try. Oh no, it's okay, more or less, yeah. B0 longitudinal modulus, yeah. So the fact is that really matter, moving matter is acting like a effective, like a magnetic field, yeah. It's then here we have transversal matter magnetic field multiplied by 1 over gamma M0 transversal modulus. Here the same, obviously, B transversal plus 1 over gamma M transversal vector, and here minus 1 over gamma modulus M transversal vector plus B transversal vector. Okay? And here neutrino left, neutrino electron right. This is what can be derived. And what we can see from this, if B 0 or mu 0, I just would like to recall that these M are proportional to rho, and rho is inverse proportional to mu, the magnetic moment. So all this M is proportional to magnetic moment in denominator. So it means that the contribution of interaction of neutrinos with moving matter is free of magnetic moments. It's cancelled out. So that means that in this equation we can write to switch off magnetic field at tau and magnetic moment. So, and let's consider this particular case when only moving matter acts in this equation. So we can write immediately the probability of neutrino electron to neutrino left-handed, right-handed as a function, let's say travel distance, equals to sine squared double theta effective. I just determined what it means. Sine squared pi travel distance x divided by L effective. So we get a usual expression for neutrino probability where sine squared double effective mixing angle equals to E squared effective divided by E squared effective plus delta square effective. Where, this is very important now, the final step of our today's discussions, mu multiplied by the modulus of the sum of two vectors, transversal magnetic field plus suppressed by gamma M0 transversal. I just say that, declare that we will deal with this particular case, but here just with strong magnetic field, yeah? And delta effective is equal to mu divided by gamma M transversal longitudinal plus B longitudinal vector. Yeah? So if you just we are insisting that we would like to switch out magnetic field and magnetic moment, then this E effective is exactly and only determined by the transversal matter current, if you remember. It's proportional to the transversal speed of electrons of background. So it means that rarely non-zero probability for electron left to be converted or oscillate to electron right exists if we consider account for or exist the effect of interaction of our neutrinos with the matter that is moving and the transversal current or transversal component of the speed of moving matter is not zero. This is very, very important and very interesting phenomenon. And just starting from the middle of the starting in the 2015, people started using this effect for analyzing fluxes of neutrinos, because the point is that you understand this is an active neutrinos, that is a stereo neutrinos. Once inside neutron star, for instance, you organize a mechanism of transition of active neutrinos to stereo neutrinos, they can freely propagate from very hot inner parts of the star and change the evolution or energy deposit or cooling of the star, you understand? Because these active neutrinos can be trapped inside due to interaction with the dense matter, and these neutrinos right-handed are sterile. They can freely propagate out of the very deep parts of the star, like just to understand why it's very important. So I think that we shall stop here, and next time I will. This is like a preamble, just introduction. Yeah, this is because this is not the whole story, but with my students, postgraduate students, just about 5 years ago, we derive and this is quite a classical description of spin evolution. But we developed the quantum approach to this effect, because in this treatment we cannot consider the change of flavor. We can only, from the Baron-Michel-Telegay equation, we can only consider evolution between left and right-handed neutrinos without change of flavor, because you cannot introduce the change of flavor. Yeah. But if you just follow the quantum treatment, as we shall do in next our 2 lectures, I suppose, we shall treat also the spin and spin flavor oscillations simultaneously and reproduce all these results for the case when flavor is not changing. Well, thank you very much.